So when I look at this, if I need to find f prime, one option is to look at this and say, well, I have one function divided by another function, so we can use the quotient rule. The other option we have is to look at this and think about rewriting it as 3 separate fractions so that each of those fractions looks like a number times x raised to a power. And either approach is totally fine. So can I get a show of hands? You can either give me a thumbs up or raise your hand or a green check mark for a yes. How many people approached this using quotient rule? I'll give you a second to click, but if you didn't finish the problem, how many people would think to start it as a quotient rule? Okay, so I got a few reactions. How many people, so let me clear those off. How many people would think to split this up as 3 separate pieces and go from there? Just trying to kind of see what the split looked like. Well, let me ask the third option. How many people looked at this and they were like, I sure wish I knew how to start that problem? Okay, maybe the rest of you are just looked at it and magically knew what the answer was. Okay, so I was hoping there was going to be a clear split somehow to decide whether I should show this to you as a quotient rule or as splitting it up. I'm going to show it to you as splitting it up because that's how I personally would approach the problem. And there weren't a lot of people that said they would use quotient rule. So looking at this, I know that I have 1, 2, 3 separate fractions if we break this up. So again, I'm not taking a derivative yet. I'm just rewriting the problem that we have. So this notation with the small 5 squeezed in next to the root there means the 5th root of x. If I write this as a fraction exponent, that would be x to the 1/5 power. And I'm dividing that by the square root of x is x to the 1/2. Moving to my next term, I have 3x squared divided by x to the 1/2. And for that last piece, I've got 1 over the square root of x, or 1 over x to the 1/2. I'm going to take one more step to rewrite this here and have some fun with fractions. So I know that if I'm dividing 2 terms with the same base, that means I'm going to subtract the exponents. So this term would become x to the 1/5 minus 1/2. And I know we talked about this before. If you wanted to think about that in terms of decimals, totally fine. And if we want to think about it in terms of fractions, also totally fine. If we stick with fractions, then that 1/5 minus 1/2, I'd need a common denominator. So I'd multiply the 1/5 by 2 over 2, and I'd multiply the 1/2 by 5 over 5. That's going to give me 2/10 minus 5/10. 2/10 minus 5/10 is giving us an overall negative 3/10. This next term, this one's a little faster for me. X squared, 3x squared over x to the 1/2. I know that's looking like 3x to the 2 minus 1/2. And 2 minus 1/2 is one that shows up often enough that 2 is 4/2 minus 1. That's going to be 3/2. And finally, this last piece, it's in the denominator, but I can bring that up as x to the negative 1/2. And after all of that algebra work, now I'm ready to take a derivative. Looking at our derivative rules, each of these now I've got a number times x raised to a power. Shouldn't that be 3x? Thank you to the. I am not sure where the mistake is. I'm going to keep going. We'll come back and see if maybe I'm okay. Okay, moving on. If I go to take the derivative right now, x to the negative 3/10, I'm going to bring that negative 3/10 down in front. And subtracting 1 from the exponent means subtracting 10/10. So I'd be at negative 13/10. On my next piece, that 3/2 is going to come down in front. 3 times 3/2 would be 9/2. And when I subtract 1, I'm really subtracting 2/2. So that'll be x to the 1/2. And on this last piece, I'm going to bring down that negative 1/2. Subtracting 1 from negative 1/2 means I'm subtracting 2/2. So I'd have negative 3/2.
Oh, shouldn't it be like minus 3x instead of?
Oh, I lost my minus sign. Got it. Thank you. I was trying to figure out where that minus, what the issue was. Thank you so much. Yes. I lost that minus sign right there. So if we were to approach this as a quotient rule, then I know as a quotient rule, I'm going to have all my parts, an f prime g plus an f g prime all over a g squared. So my denominator of the square root of x, I'll just put it in there. I know that here I'm going to leave that square root of x alone, but this would need to be the derivative of the numerator. Well, either way, I still have to think about that 5th root of x as x to the 1/5, so that I can take the derivative here and get 1/5 x to the negative 4/5 minus 6x plus 0, because the derivative of 1 is going to give us 0. Over here, I'm going to leave f alone, so I'd have x to the 1/5 minus 3x squared plus 1. And the derivative of the bottom, if I think about that as being x to the 1/2, I'd have 1/2 x to the negative 1/2. Now, I would say that if the only thing you have to do is to take the derivative, this isn't necessarily worse, right? For me, I'd rather spend a little bit more time doing the algebra, but that's because I'm pretty comfortable with the algebra. And if I had to simplify this, that looks terrible. Because if I had to simplify this, now I'm having to distribute that out to each term and then divide every term by x. So for sure, if I have to simplify it up front. So I'm always going to start by finding the places on the graph where I am 100% sure that I know what the slope is. And that's going to be anywhere that the slope looks like it's 0. So I am looking at a slope of 0 up here, right here, right here. And there's one more place where the slope is getting pretty flat, and that's out here on the end. So at each of those places, if I'm going to sketch a graph of the derivative, I know that at those x values, I need my derivative graph to be equal to 0. So here, and I'm just going to write that out. So this is an x of negative 1 and a slope of 0. And this is an x of 0 and a slope of 0. And this is an x of 2.5 and a slope of 0. So unfortunately, he's making us draw our f prime graph over here. I really prefer to have it directly down so that I can just transfer those x's down. But if I have to do it over here, then it's helpful for me at least to have labeled on this graph what the x values were. So when x equals -1, I need my f prime graph to have a value of 0. Same when x equals 0, and the same when x equals 2.5. And then I also know on this side of the graph, I'm expecting it to level off at 0. Now, the next thing that I want to do is to look for places on the graph where our slope is changing. And by changing, I mean like where I'm going up or going down. So for example, right in here, if I had to estimate, that's a slope of about 1, a positive 1 slope. So here when x equals -2, I'm estimating that slope is approximately equal to 1. When I come over to this graph, that means when I'm at an x value of -2, my slope is up here at about a value of 1. Now right in here at x equals -1/2, I'm looking at a slope of about -1. So if I come over here to x equals -1/2, that slope is about -1. And looking at this, that slope right there, when I'm at an x value of -2, that's really the steepest slope that we hit. All of my slopes over here are positive, but less steep. And the same with my slopes between -2 and 1. They're all positive, but they're less steep. So if I think about that numerically, I know that on the edge, I should be approaching a slope of 0 because this is flattening out over here. I know that at x equals -2, that's my steepest slope or my largest slope I'm going to hit. And then between -2 and -1, or actually between -2, between -2 and 1, my slopes continue to be positive, but they're leveling out to 0. And then between -1 and 0, all of these slopes are negative, with the steepest negative slope happening there at about -0.5. So that's my steepest negative slope. So it's the lowest point I'm going to get to on my slope graph. Now let's talk about this piece. So if I look in here for where's the place where I have the steepest positive slope again, that's maybe right about there. I'm going to estimate that to be about 1.5 on my x-axis. So at an x of about 1.5, I'm getting to a steep slope again. And looking at the graph, these two seem to be about the same slope. So I'm expecting when I'm at an x value of about 1.5, I'm going to get up to a slope that's about as steep as my steepest slope was at an x value of -2. I know that between the x value of 0 and an x value of 2.5, all of these slopes are positive numbers. So they get to the steepest positive value and they start to flatten back out again to 0, but they always stay positive between 0, an x value of 0 and 2.5. So I'm going to look something like that. Now on the right-hand side of 2.5, once I get past that, these slopes are all negative, and it looks like they're just getting steeper and steeper negative-wise. So for as far as we can tell, they're negative, so they need to be below the axis here, and all of those slopes are getting like more and more negative. And that's kind of the extent of what we know. So there's my f prime. So if chain rule is not an option for us to find f prime, then we really need to rewrite this. That exponent up there, that cosine cubed, means, and I'm not taking the derivative yet, I'm just rewriting it, This means that I have 3 cosines multiplied together. That I have cosine of x times cosine of x times another cosine of x. Since I have 3 things multiplied together, we're going to need to use our triple product rule in order to find this derivative. So if I think about this as an f times a g times an h, then for our triple product rule, which Kuba does expect you to have memorized, for the triple product rule, I've got an FGH, an FGH, and an FGH. So for our triple product rule, I've got 3 letters, an F times a G times an H. So FG, so I'm going to write it 3 times because we had 3 letters. What usually goes with multiplication is addition, and I already put that addition in there, and then I'm going to chase down the derivative. So f prime, the derivative of cosine is negative sine. Then I would copy the cosine down again and copy the cosine down again. Here, we're going to leave the first piece alone. I'll take the derivative of the second piece. Derivative of cosine of x is negative sine of x, and leave the last piece alone, cosine of x. On my third term, it's the third piece that I take the derivative of. So I'll leave the first piece as a cosine, the second piece as a cosine, and when we take the derivative of that third piece, we get negative sine of x. Now you can choose to leave it here and walk away, but we can also simplify this. And this is going to get back to the question earlier about chain rule. From each of these 3 pieces, each of them has a negative sine of x, and each of them have a cosine times another cosine. So if I think about that cosine times cosine as a cosine squared x, if I were to factor that cosine squared x out of each term, then from this piece, I'd be left with a negative sine of x. And from this piece, I'd be left with a negative sine of x. And from that third piece, I'd be left with a negative sine of x. Well, negative sine of x minus sine of x minus sine of x can also be written as negative 3 sine of x. So I'd have negative 3 sine of x times cosine squared x. That first warm-up problem that we started with, the reason that we were able to use some algebra to break the pieces up is that the top was all a number times x raised to a power, and in the denominator, we had a single piece. Here in my denominator, I don't have a single piece. I've got this x minus 1 thing, and on top of that, I've got trig upstairs. So if I got trig in my numerator and x is elsewhere, we're really stuck with a quotient rule. If I'm going to do a quotient rule, I personally start by getting all my pieces ready. Partly because I am a slow test taker. Doing this means if I don't have a chance to finish the problem, at least I demonstrated that I know what the quotient rule is and that I'm supposed to do it for this problem. Now I'm going to pop in and do all of our pieces here. So I need an f prime times a g. I put a plus there and nobody stopped me. Well, we're good with my minus signs earlier. Minus f times g prime. Okay, in the denominator, I keep that x minus 1. We're just going to square it. When I take the derivative of the top, I did not leave myself enough room to write here, but we'll live. The derivative of secant of x is secant of x times tangent of x. To that, I really didn't leave myself enough space. To that, I need to add the derivative of x squared, so I'll have plus 2x. Then I'm going to leave the denominator alone. Here I'm going to leave the numerator alone and have secant of x plus x squared, and then times the derivative of the bottom. And the derivative of my denominator is 1. And then I'm going to walk away. Similarly to my warm-up problem, I am going to start by writing this as x's raised to powers. So before I take a derivative, I'm going to rewrite this. Now the cube root of x squared, that cube root means it's a 1/3 power, and the fact that it's in the denominator means it's going to be negative. So overall, this is going to look like x to the negative 2/3 power. And my guess is that is exactly where the question was in this problem. So to do that kind of in slow motion, if I have 1 over the cube root of x squared, there are a lot of different ways to approach that. But the first thing I would do is to deal with the 1/3 power and say that's the same as x squared to the 1/3. Then I can move the whole thing up by making that a negative 1/3 and saying that's x squared to the negative 1/3. And then a power raised to a power means that I would multiply those together. And that's how I got to x to the negative 2/3. Now that we've got that simplified out as x to the negative 2/3, now our derivative is going to be more straightforward. Bring down that exponent. Subtract 1 from the exponent. So negative 2/3 minus 1 is going to put me at negative 5/3. And the derivative of negative x is negative 1. We've been told to evaluate this when x equals negative 1. If x is negative 1, then we're really going to have to keep track of all of our negatives. Now, remember, I can't take the square root of negative 1, but the cube root of negative 1 is just fine. So when I put in here negative 1 to the negative 5/3 power, I'm going to treat this as if I've got two separate things going on. I'm basically going to take this back to sort of thinking about it more in this notation. So negative 1, let's see if this shows up okay today. Negative 1 to the negative 5/3 power. There's all kinds of stuff going on in there. The first thing that I'll take care of is to separate this out to be negative 1 to the 1/3 and then to the negative 5th power. Well, negative 1 to the 1/3 is asking me for the cube root of negative 1. Negative 1 times negative 1 times negative 1 is negative 1, which means the cube root of negative 1 is negative 1. Now I've got that negative and the 5th power. I'll deal with the 5th power first. So if I have negative 1 to the 5th power, negative 1 times negative 1 times negative 1 times negative 1 is negative 1. I now have negative 1 to the negative 1 power. Well, that's the same as 1 over negative 1, and 1 divided by negative 1 gets me negative 1. Whole lot of work for a really boring answer. Back around to here. Oh, did you have to show any of that work? Heck no, but you have to be able to do it. So if you can think through all of that in your head, great. So I'd have negative 2/3 times negative 1 and then minus a 1. Multiplying here, negative 2 times negative 1, I'd have a positive 2/3 minus 1. Sounds like negative 1/3 is my final answer there. Oh, was that a question? No, sorry. Okay. Anytime we are looking for the equation of a line, I always have to have two things. I need a slope and a point. Well, here, the slope word that we've been given is perpendicular to, which I know means we need the opposite reciprocal of the slope. So I'm going to hold off on that for a second because that's going to require some work. I'm going to start by finding the point. Well, if x equals 4, that's only half of a point. I also need the y value. So if x is 4, then the y value at 4 is going to look like 2 times 4 minus the square root of 4. So I'm looking at 8 minus 2. That looks like a 6 to me. So again, in the spirit of partial credit, because I am slow on exams, I am going to go ahead and show someone, hey, I know what I'm supposed to do. I know I'm supposed to write the equation of a tangent line. I got started. Now to find this slope, we're going to start by finding the slope of the tangent line and then do the opposite reciprocal. So for the slope of the tangent line, we're going to need a derivative. And I'm going to choose to rewrite that square root to say x to the 1/2 power. And when I take that derivative, I'll get 2 minus 1/2 x to the negative 1/2 power. I care about the slope when x equals 4. So I'm going to find the slope of the tangent line at x equals 4. 2 minus, and here we're also going to, similarly to the problem we just did, we're going to have to deal with a number raised to a negative fraction exponent. So I've got 1/2 times 4 to the negative 1/2. I'm going to deal with the 1/2 exponent first. A 1/2 exponent means we're taking the square root. The square root of 4 is 2. Then I've got that negative exponent. So instead of being a 2, it's going to be a 1/2. So I'm looking at 2 minus 1/2 times another 1/2. If you were really pushed for time on the test and your brain was like, I can't think fractions right now, here's my genuine advice. A 1/2 times a 1/2 you can probably handle. That's 2 minus a 1/4. If you really are like, I can't think fractions, I've just got to get through the next problem, I'm going to come over here and write y minus 6 is equal to negative 1/, and I'm just going to write the whole dang thing, 2 minus a 1/4. You're not wrong. You have mathematically correctly done this problem. You just didn't simplify it. Now, your TA is not expecting to see that answer. The answer your TA is expecting to see is the 2/4 minus 1/4. That 2, if I multiply it by 4/4, that's 8/4 minus 1/4, or 7/4. So your TA is expecting to see an answer that looks more like y minus 6 is equal to negative 4/7 x minus 4. So if I'm looking at 2 cosine 3x is equal to 1, my first step is to isolate the trig piece. And I will say that if we had multiple trig functions in the problem, then my first step would be to make sure that they all have the same thing inside of them. But here, like if I had a cosine of 3x and a cosine of 2x, then the first thing I would need to do is use trig identities to get them both to be cosine 3x or both to be cosine 2x. But here I just have a single piece. Since I just have a single trig piece, I want to isolate that trig piece by itself. So I'm going to divide both sides by 2. Then I'd be looking at cosine of 3x is equal to 1/2. My next step is to identify what the reference angle must be if we're going to be at, if cosine is equal to 1/2. If you got your unit circle handy or memorized, great. I always go back to my right triangles. So if that's a 2, then when I cut it in half, that's a 1. I've got a square root of 3 for the height. And because this was an equilateral triangle, I know that right there is pi/3. If cosine is going to be 1/2, I am looking at an angle of pi over 3. So thinking about that, that means this part in here, that 3x, that's my angle, would have to be equal to pi over 3. But that's not my only answer. Oh, by the way, that would mean that x is equal to pi over 9 when I divide that over. But that's not my only answer. For starters, cosine is equal to 1/2 in another quadrant. So if I were thinking about cosine being equal to 1/2, well, cosine is positive in both the first and the fourth quadrants. So cosine would be equal to 1/2 down here in the fourth quadrant. I don't actually have to worry about that though, because this told us to stop at pi, but we're not done. And here's the reason we're not done. Rather than thinking about this as a unit circle, if I think about this as the function cosine 3x and what that graph would look like, if y is equal to cosine 3x, normally, that is really crooked. Normally, I think that's better. Cosine has a period of 2 pi. Cosine starts up here at 1, and it would complete a cycle normally in 2 pi. However, that 3 in front of the x has modified the period. The period of this function is 2 pi divided by 3. So here I'd be at 2 pi over 3. I'm not quite to pi yet. Pi would be at 3 pi over 3. So I've got to keep going with my curve. So there's the 2 pi over 3. By the way, that means that right here in the middle, that would be pi over 3. And I've got to keep going to here in order to be at 3 pi over 3. So I am in fact expecting 3 solutions to this problem. Because if I'm now looking for where is that cosine of 3x equal to 1/2, I'm looking at where the y value on this curve is equal to 1/2. And we found this one at pi over 9, but we didn't find either of these yet. So I know that we should end up with 3 answers. So now I'm going to take us back around to that unit circle piece. Even though it feels like getting into the fourth quadrant wouldn't be on 0 to pi, the issue is that because this function has a different period, that point right there kind of represents where we are in that fourth quadrant if the period were normal. So I'm going to go back to my unit circle. And this is 2 pi. But because my reference angle was pi over 3, I'm actually going to write that instead of as 2 pi, I'm going to write that as 6 pi over 3. So that fourth quadrant answer that was going to give us a positive cosine is 5 pi over 3. So if I come up here, I had 3x is equal to pi over 3 or 5 pi over 3. And even though that's bigger than pi, it's okay because that's not our x value yet. But when I divide by 3 over here, I'm going to be at 5 pi over 9. And this one hasn't gotten us to pi yet. So now we found our pi over 9 and we found our 5 pi over 9. But I need this last one, and this last one is exactly 1 period away from that pi over 9. So that last solution is going to be pi over 9 plus 1 period, 2 pi over 3. Now, in order to add those together, I'm going to need a common denominator. So I'll have to multiply this guy by 3 over 3. And I'm looking at 2 times 3, that's a 6 plus 1 more. So I'm looking at 7 pi over 9. And those would be my 3 solutions to this question. We can handle the algebra. So what I do want to do, because I know how messy this algebra is going to get, on the side over here, I'm going to work out what f of x plus h is and simplify it before I plug it into the formula. When I go to find f of x plus h, I'm going to be looking at 2 times x plus h squared minus 3 times x plus h plus, oh, I said the 3 and I didn't write the 3. Let's try that again. Minus 3 times x plus h plus 7. Well, multiplying all of that out, that makes my f of x plus h. X plus h squared, when we FOIL that out, we get x squared plus 2xh plus h squared. And I'm going to go ahead and distribute in the 2. So I would end up with 2x squared plus 2 times 2h, or 4xh, and then h squared, but again, multiplied by 2. So I'll have 2h squared. Then we're subtracting off a 3x, subtracting off a 3h, and adding 7. Good times. So this whole thing is what I'm plugging in for the f of x plus h part in our limit. So I got all that. 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 7. And from that, I'm subtracting off my f of x. And I'm going to be careful to put my f of x in parentheses. 2x squared minus 3x plus 7, whole thing over h. Our goal, whenever we're doing these limit definition of the derivative problems, is that somehow the top is going to simplify so that I can cancel out that h that's in the denominator. I'm going to take that minus sign and distribute it through over here by the magic of my eraser. So when I distribute the minus sign through, this is going to become 2x squared minus that minus will make this plus, and then distributing my minus sign in there will make that a minus 7. And now I'm looking for all of the things that I can cancel out. So that positive 7 and that negative 7 will cancel out. That negative 3x and that positive 3x will cancel. The 2x squared and the negative 2x squared will cancel. From what is left, I now have an option either to factor or to write it as separate pieces. I don't think it really matters, but let's go ahead and factor. And if I factor, the thing I'm trying to factor out is an h. So from 4xh, if I pull an h out, I've got 4x. From 2h squared, if I pull an h out, I have plus 2h. And from that negative 3h, if I pull an h out, I have negative 3. My h over h is equal to 1, and I'm ready to apply the limit, meaning I'm going to plug in 0 for h right here. And I'll be left with 4x plus 2 times 0 minus 3, or 4x minus 3. Now, I should have done this at the beginning, but we already knew what the answer was going to be. We're trying to find the derivative of this. So if the question was just to find the derivative of this, I'd look at that and go, oh, great, 2x squared, I'm going to bring down the power. 2 times 2 is 4, subtract 1 from the exponent, so I'd have 4x. Boom. Negative 3x, take the derivative of that, I'm just going to get the negative 3. Great. And the derivative of 7 is 0. Awesome. Doesn't show up. Didn't need to be there. Perfect. We got our derivative. So let's start with a graph of 1 over x. And that is one of our parent functions that we should definitely know what that graph looks like. So there's a graph of 1 over x. And it definitely, the graph does not contain the point 0, 1, right? Because this graph actually has a vertical asymptote there at 0. So we're here at the point 0, 1. And we are looking for a tangent line to this graph that goes through that point. We're not looking for a tangent line at that point. We're saying if I sweep along this curve looking for tangent lines, one of those tangent lines to the curve is going to pass through the point 0, 1. And I think that's about my best visual there. That tangent line looks like it's going through 0, 1. Now it says to find all of the points. Now looking at this, I think there's also probably maybe a point down here that goes through that point. I'm not sure. Thinking about those tangent lines. Yeah, maybe not, because this tangent line would get vertical. So I think that might be our only one. So we're looking for, what is that point right there? X comma y. What the heck is that point? Well, let's see what we know. I know that this is supposed to be a tangent line, and we do know how to find the slope of a tangent line. We're going to find the slope of the tangent line by taking a derivative. I also know that because I've drawn in this tangent line, and I've drawn in 2 points on that tangent line, I know that the old school slope for this line has to be the same as the slope that we get when we take the derivative. Meaning the slope between these 2 points has to match up with the slope of the tangent line. Let's get going. So let's go old school slope. So if I go old school slope, I mean change in y over change in x. So old school slope is going to look like y minus 0 over x. Oh, sorry. Y minus 1 over x minus 0. That's my old school slope between those 2 lines. Well, I'm going to set that equal to my new school slope, my calculus-y slope. If y equals 1 over x, then that's the same as x to the negative 1/2. I mean, x to the negative 1. I wrote the correct thing, which means that y prime is going to be negative x to the negative 2. So I need this thing to equal negative x to the negative 2. And now I got a problem because I have one equation with 2 unknowns in it. I don't know the x value or the y value. One equation, 2 unknowns. Oh darn, I sure hope we know something else. Secretly, we do know something else because y is equal to 1 over x. So I could have labeled this point on the graph, instead of labeling it as x comma y, I could label that point as x comma 1 over x, because that's how we get the y value. So I'm going to replace the y in our old school slope with a 1 over x. Now from here, the algebra gets messy, but hang with me for a minute. So first of all, x minus 0, I can just leave that alone. I've got 1 over x minus 1 all over x. Now let's actually clean that up a little bit more. Looking at the numerator here, if I'm subtracting fractions, I can get a common denominator with that. So I'll think about that 1 as really being x over x. So that in my numerator, I've got 1 minus x over x. And then that whole thing is over x. Over here, I'm going to choose to rewrite this to be negative 1 over x squared. Lots of different paths through this, but this I'm going to clean up to be a single fraction because dividing by x is the same as multiplying by 1 over x. So really, I've got 1 minus x over x squared is equal to negative 1 over x squared. That's convenient. Everything has the same denominator. That must mean that 1 minus x is equal to negative 1. I can add the 1 to both sides and add an x to both sides so that I end up with 2 is equal to x. Which is almost the answer because it asked us to find all points x comma y. So I know what the x value is now. But the point is going to be 2 comma 1/2.